On today's episode, we'll be looking at the properties of mass and weight. Many people often describe mass and weight to be one and the same. Now, don't get that confused. They are not. They are actually two different properties. Now, mass can be described as a resistance to change in its velocity, or we can say it's inertial mass. On the other hand, we can also look at it as saying it's a source of gravitational changes in velocity. In that regard, we can say it is gravitational mass. Both of these masses were described by Galileo Galilei, the Italian physicist. Galileo Galilei was the first person to formulate coherent thoughts on inertial and gravitational mass and their equivalents. His insights were based on experiments with rolling balls and inclined planes. This all happened early in the 17th century. We can look at throwing a cricket ball versus throwing a tennis ball. Now, what is realized is that when you throw a tennis ball, it is thrown easily. However, you cannot throw a cricket ball as easily. You have to apply more force for it to speed up to the same velocity as tennis ball. This is simply because the cricket ball has a lot more mass than the tennis ball. Weight has a lot to do with gravity. Now, an object's weight tells us how hard the force of gravity is pulling on it. Weight and mass are related. The amount of mass an object has is the amount of force or weight is applied to it. However, that's not the only factor. Isaac Newton figured out that the force of gravity between two objects is proportional to the product of the masses of the two things and the inverse square of the distance between them. In other words, the further apart two things are, the weaker the force of gravity. Alright? In this experiment, we'll be using objects of unknown masses, objects of known masses, an electronic balance, a triple beam balance, and a ruler-sized pegboard. For the experiment, we simply set up the triple beam balance ready to weigh the known masses first. Then we add each known mass to the triple beam balance, carefully adjusting the sliders of 100 grams through to 10 grams until the mark to the far right is in line with the indicator. Now bear in mind, the masses are recorded at each interval. We can put these down in a table for later analysis. To find the mass of the object on the pan, we add the masses to the pan and move the sliders until the indicator lines up with the marker to the right. What is done is very simple. We add the numbers from the three beams to get the overall mass of what is on the pan. For the masses of the unknown objects, we simply add them one by one and move the sliders of the triple beam balance until the indicator is lined up perfectly with the mark to the right. We do these one by one as we are not sure of the masses of the unknown objects. If you are noticing any fluctuation in the triple beam balance, simply move the sliders, either the 100 gram through to the 10 gram, so to have both marks line up as best as possible on the triple beam balance. We then tabulate the results just as before. And to gain an appreciation of the masses, we also use an electronic balance. Now, for the unknown masses, they are only used with the electronic balance and not the known masses. We start off by zeroing the electronic balance and then adding the unknown masses one by one at an interval. We use the equation weight is equal to mass multiplied by gravity to find the weight of each of the unknown masses